Okay, should we get started? Are you ready, Chen?
Yeah. Yes.
Okay,
Yeah.
great. Okay, welcome everyone to this week's CDAC webinar talk. It's a pleasure this week to introduce our colleague Chen Li from the University of California at Riverside. Chen specializes in scattering techniques with both neutrons and X-rays, including the applications of those methods to experiments at high pressures and variable temperatures, along with related techniques, including theoretical techniques. Chen obtained his PhD in material science from Caltech in 2002, and then moved to the spallation neutron source at Oak Ridge, where he was part of E-FREE, the Energy Frontier Research Center that we managed at that time. In 2016, he joined the Department of Mechanical Engineering and Material Science and Engineering programs at UC Riverside. And there he's continued a lot of this work in scattering. And today he'll tell us about his most recent work involving inelastic X-ray scattering. So welcome, Chen.
Thank you, Ross, for the introduction. Yeah, it's glad to talk about my work in the CDAC seminar. As Ross mentioned, I used to work for E-FREE, so it's glad to see many familiar faces or names here. So before I start, I want to, let me see. Okay, yeah. So when I run into people in conferences, they usually ask me, where is UC Riverside? So I think I would put this slide just an introduction. So we're actually not too far away from downtown Los Angeles. It's about an hour drive to the east into the desert. So as you can imagine, we're in Southern California, we're in desert, so we have very hot summer, we have kind of cool but a little bit wet winter. And we are not too far away from Big Bear, and we are within an hour drive from the coast if there is no traffic. And we are reasonably close to Disneyland. So in case you guys are visiting Southern California, stop by. And it's great if some of you can give a seminar visiting us. And we have a pretty sizable campus. It's still heavily under development, as you can see from maybe some of the pictures, photos here. But we welcome you to visit us whenever you can. So I want to give a very quick summary of what we actually do in my group. As Russ introduced, we work heavily with scattering techniques. Lots of them involving neutron scattering, but we do some X-ray scattering. And here's just a brief list of what are the ongoing projects we are working on. And I have a few different figures on the right-hand side showing some of the ideas that we are working with. One direction we're working on right now is magnon-phonon interactions. And you can imagine that both magnon and phonon in periodical system forming dispersion relations, and a lot of them actually strong correlate with the two. In a lot of materials, the two systems actually are strongly correlated. And for example, I'm showing the case on the right-hand side. Let me put this. Okay, so as you can see here, this is one of the dynamic structure function we measured with inelastic neutron scattering, showing one of the antiferromagnetic system where the spin wave actually correlates really well with phonon dispersion. So we're trying to see a large interaction between those. And we also look at some exotic spin dynamics, as you can see in this figure. And here we actually are showing some kind of spin wave continuum that span between the two magnetic Bragg peaks. And this is actually one of the magnetic frustrated square lattices. It's actually rare for square lattice to have frustration, but this is, we believe this is a system we observed it. We also work with lattice thermal transport by both neutron scattering and working with inelastic X-ray scattering, but also we do some of the high pressure thermal transport measurement. This is in collaboration with a colleague also at Riverside. We use time domain either thermal reflectance our time domain MOC, which is a magneto-optical Kerr effect, by looking at thermal transport under pressure. This part work is done in diamond envelope cell. But today I'm going to focus on two parts of my work that heavily rely on elastic scattering. One part is the phonon in low dimension materials. We actually do this part of work also with both neutron and elastic scattering. And with neutron, we look at more on the nanoparticles, and by looking at the phonon confinement effect and phonon interactions involved in those nanoparticle systems. But we do use elastic scattering to look at layered materials, and this is which I'm going to spend some time talk about today. I'll also look at phonon chirality and phonon angular momentum, this is also an elastic scattering work. And many of the components in our work actually rely on high pressure. And we start doing more and more high pressure neutron scattering, either by diffraction or neutron scattering. But as you can imagine, it's still difficult to achieve sizable high pressure using neutron techniques. So we still rely on lots of those synchrotron work by using traditional diamond envelope cells. Okay. So let's see. So here's a brief outline of my talk today. I'm going to spend about 2 slides, give you a brief background on what elastic scattering is and what the beamline we work with. And then I'm going to talk about more on the lattice dynamics part of 2D van Waals materials. And then the rest of the talk, I will start talking about some chiral phonons and some recent work we did. And the last part of the work is actually still heavily in development, and we are still working through a lot of the fundamental part and try to understand the data we saw, but I will want to share some of the data. Okay. And as you know, we use scattering tools. So I borrowed these slides from European spallation neutron source by showing what are the energy scale and time scale we are talking about. As you can see, those colored areas actually are the focus of neutron scattering, either time of flight or triple axis elastic neutron scattering. But for elastic X-ray scattering, we cover energy and length scale region that's actually quite related to elastic neutron scattering. And there are some advantages you can quickly see that we are able to probably certain energy and length scale that is not well covered. For example, in this region, where the energy is actually excitation of the energy of the excitation are relatively large, but the wavelengths are relatively long. Okay. But on the other hand, they are cover similar domains. And what we do, most of our experiments on sector 30 at APS is a Hurwitz beamline. And there are some advantages of elastic scattering, and I summarize it here. And we are able to work with smaller single crystal sizes, which is actually a big limiting factor for elastic neutron scattering, since we usually need a gram or tens of grams inside of single crystal for for reasonable neutron scattering work. On the other hand, we can work with much smaller sizes of crystals with elastic X-ray. And also elastic X-ray has lower background and is considered a cleaner method. And we also have more flexibility in terms of scattering geometry, since we usually can put the sample on a 4-circle stage, which allows more freedom than degree of freedom than we can achieve usually on a neutron beamline, where we have to be more hands-on if we decide to change the scattering geometry. And the sample environment allows us to work with higher pressure, which is one of the important benefits of elastic X-ray scattering. And we also have a different scattering intensity depend on elements in comparison with neutron scattering. So that allows us sometimes to do a combined neutron and elastic X-ray work to allow us to decompose a contribution from different elements. Okay, so But one thing that which is usually not discussed much is about polarization. With X-ray, we do have control of the polarization in principle. And even though neutron does have its own polarization, but that polarization is different. That usually comes from the magnetic moment carried by neutrons and the spin. Basically, the spin of the neutrons. And that is different from what we are talking here in terms of in-lux X-ray scattering, okay? So here I'm showing a photo of the Hurwitz beamline. Sorry, there's actually a typo here. We shouldn't have S there. So this is a photo of one of my students taking at the beamline and while we are doing one of the experiment. Here I'm showing the one phonon's dynamic structure factor, which is actually something we're going to come back later when we start talking about scattering of phonon with angular momentum, okay? And of course, all the work won't be possible without the very support beamline scientists. In particular, we're working with Ayman and Ahmed, and also Thomas helps a lot working with the second part of my talk, where I'm going to talk about the chiral phonons, which we are working on at the moment. So now let's move on to the second part of my talk. I'm going to go through some of the recent lattice dynamics work we did with 2D van Waals materials. This part of work is done by two graduate students, and some part was in collaboration with my collaborator in Beijing. And actually, Bing is visiting from his group for part of the work, but most of the work were performed during his stay here. So let me give you a little bit background on van Waals interactions in 2D materials. Many of you are probably already familiar with, but what we do know is van Waals interactions are very exist in many layered compound, and that gives very weak coupling between layers, and sometimes allow exfoliating those layers into mono or multi-layers. So we actually going to come back to this later. It turns out this interaction is actually weaker than many people would probably think about for in terms of phonon dynamics. And it turns out we actually observe a lot of dynamics that's actually similar to what a monolayer would show. Also, the van Waals interaction plays important roles in many physical phenomena. I'm not going to go through the list, but they are important. And also they have a lot of potential applications because they allow basically manipulating single layer, monolayer, and produce devices out of fabrication by overlaying those maker heterostructures or working with their interfaces, okay? But the direct measurement of the van Waals interaction usually is tricky since they involve very measurement at small length scale and small magnitude. And a lot of time you can figure out its mechanical properties using atomic force microscope by working with small layers. But those are, I would say, not very effective in determining lattice dynamics. So that's why we're using X-ray to look at those. Okay. And here I'm trying to show one of the systems we're working. Oh yes, here's a more overview of what type of systems we're looking at. And we look at palladium selenide and tungsten selenide. And the tungsten selenide is probably one of the most well-studied transition metal Dichalcogenides. And since they have a lot of potential applications for either for spintronics or for microelectronics, and also it shows many interesting photonics or electronic or ferroelectrical or even thermoelectrical properties. And as you can imagine, those materials are all 2D van Waals bonded loose layers, and they actually pose a big challenges to understand their temperature behaviors. And what we need to do is we usually need to load those samples inside the diamond cell and apply pressure, and we do in-lux X-ray scattering. And for in-lux scattering, we are very much limited working along the axis of the diamond envelope cells. And that poses a big constraint in what are the region of the burden zone we can explore by how the samples are oriented inside this diamond envelope cell. So as you can imagine, for those 2D van der Waals materials, it's relatively easy to put the stacks put the atomic layers in the direction that is perpendicular to the axis of the beam, which means if we look at the material itself, usually the beam comes from the top, and that allows us to probe the phonon dynamics along certain high symmetry direction in the reciprocal space. The problem is, if we do want to look at the van der Waals interactions, usually we have to look at the flexor mode, which are actually the mode propagating in plane, in the basal plane of those atomic layers. That means we have to mount the sample 90 degrees from where its natural loading direction would be. And this usually is done by making a small slice of the material along one of the high symmetry lattice axis, and then we turn it 90 degrees and load it inside the diamond envelope cell. Now here comes the tricky part. Usually this loading is very difficult, as you can imagine. Most of the time when you try to cut a very soft and delicate material like the 2D van der Waals compounds, you end up destroying the structure completely. And this is not hard to understand because we are cutting along the direction that is not its foliating direction. So you can imagine that we are trying to cut a cake, a layered cake, and with very loose bonding in between the layers. And we want to make a very thin slice, but very thick stack. And usually you can imagine when you cut it, the thing fall apart into pieces. And that did happen to us multiple times. And it turns out we have to try loading this sample over 100 times until eventually we think, oh, it might never work. And we probably just deal with it and we work only in the symmetry that is practical for loading. But it turned out we are lucky. In one of the last trial we tried, we actually load the sample in the symmetry, in the geometry that has the layers perpendicular to the beam. But after gas loading, somehow the sample flipped up. And this turned out to be a good sample. So we were able to probe the phonon lattice dynamics actually in plane along the direction of the in-plane layers. Okay. So here I'm showing some data, and this is our measured in-lab X-ray data. For this one, this is performed under ambient conditions, so no pressure for the moment, and we overplotted on top of our DFT calculation. And you can see that it actually grades reasonably well. In particular, if you look at along gamma X, which is the panel A shows, and gamma Z, which is panel C shows, most of the phonon branches grades pretty well with a harmonic calculation. And the model actually works pretty well. And even the van der Waals interaction seem to be predicted well by the, when we are using one of the PD potential, which include van der Waals component that used to describe this van der Waals interactions. And the only major difference is what we saw was along the gamma Y direction, which is one of the in-plane high symmetry direction. And this ZA mode, this turned out to be one of the flexor mode that corresponding to the atom vibrating outer plane, but the propagating vector is along in the basal plane. And this flexor mode, as you would expect from the DFT calculations, show a nonlinear behavior. That's kind of also expected since usually those flexor mode are highly unharmonic, and since the outer plane vibration that cause a non-harmonic potential for that particular phonon mode, and also the phonon dispersion itself seems to show usually a quadratic type of dispersion relation. And the one thing we did observe that we think could be interesting is when we try to extract the phonon line width, which will tell us the information on the phonon lifetime in this material, we find that it turns out this ZA mode, this flexor mode, has a quite narrow phonon line width. As you can imagine, in-axis scattering doesn't have very high energy resolution, so a lot of the fittings probably won't tell you much, since our instrument resolution is usually on the order of MeV, but it does clearly indicate that we have narrower phonon line width for this ZA mode in comparison with the others. So we don't know exactly what line width is, but we do know that it's narrower. And this is kind of interesting to see. And let me see, okay. So now we load the sample in the pressure cell, and we, as you can tell, that we didn't go very high in pressure, simply because usually the van der Waals interaction are relatively weak, and to prove that we don't need any pressure that is above, in this case, 6 GPa. So we went as high as 6 GPa, and actually through across the phase transition around 5. And this was previously characterized before, so nothing new, but it's good to see that when we were doing in-lattice secondary scattering, we can reproduce the more or less the lattice parameter that what the prior measurement tells us. And we do see a phase transition that's between 4 and 6 GPa, and that is in good agreement with the prior result. And usually those in-lattice secondary scatterings, in-lattice secondary spectrometers are not good diffractometers. So you cannot get the best resolution in terms of lattice parameters. But what we do tell is we see the lattice quality doesn't got damaged much through the pressurization. Okay, and in the two figures I'm showing here, I actually have a red arrow that's pointing to the Bragg peak we're going to carry out most of our in-lattice secondary measurement with. So the phonon dispersion measurement will be performed near the vanicity of this peak, and they are different Bragg peaks at different phases. But if we try to index, well, if you try to use a similar symmetry as in the lower symmetry phase for the high symmetry, those are actually the corresponding Bragg peak, and we can actually do comparison between the phonon measurements we got at those two similar burning zones. Okay. So here are some pressure measurements we did on palladium selenide. And I'm showing the results again plotted over DFT calculations. And we performed the pressure measurement from ambient up to 6 GPa across the phase transition. And here's a few things I want to show first. The first thing is for TA and LA mode, the agreement actually pretty reasonable, as you can see in the panel B and panel C. And there are some small disagreement between the calculation and the measurement, but I would contribute many of them to be either the potential itself, or there could be different lattice parameter predicted by DFT versus what you would expect under the pressure in the real system. But they are actually pretty good in terms of first principle simulation. There is a significant difference between two phases, but that's also expected because we have a phase transformation, and now the phonon would behave quite differently once we reach 6 GPa. But the main interesting result we see actually shown on the panel A, which shows this ZA mode, which is a flexor mode I was referring to. So as you can see, initially we have a relatively kind of flexor mode, which showing a nonlinear behavior in dispersion. It's actually not exactly quadratic. It's actually something in between. And once we apply the pressure, you can see this branch actually stiffens slightly initially. But once we reach the pressure around 3.7 GPa, the phonon actually stiffens a lot. And something happened between those two pressures. But this is still in the low symmetry phase. And at even higher pressure, now this, again, after the phase transition, the DFT were able to produce it pretty reliably. So some quick conclusion you can come up with this is, okay, something is going on when we apply pressure, and something actually happens in intermediate pressure there, well below the phase transition. And the van der Waals bonding behave more like a covalent bonding once we are up near 3.7 GPa. And additionally, this flexor mode probably going to be quite harmonic, because this kind of nonlinear behavior when we apply pressure is not something we would expect in a harmonic or quasi-harmonic system. And this agreement generally is better for tetragonal phase, which is a higher pressure phase. And in this case, we no longer have van der Waals interactions between the layers. So we try to do some extract more information by fitting the acoustic phonons. And here is basically we are enlarging the phonon measurement, acoustic phonon measurement along this gamma y directions. And what I'm plotting using the green curve here is what you would expect from an ideal monolayer structure. And on the other hand, if you look at covalent system, you should expect phonon to be more or less linear. So to be more or less linear, as you can see by this tetragonal calculation, tetragonal results under 6 GPa. So turned out most of our measurements falls in somewhere in between. So if we fit it with this function, which energy will be proportional to wave vector to the power of beta, and this beta will fall somewhere between 1 and 2. It turns out if we do that fitting, for a lot of the pressure, at least the lower pressure, this value is very close to 2, somewhere around 1.8, until we increase the pressure to be close to the phase transition, but still below the phase transition. And this actually is consistent if we try to fit this model with a more elastic or a continuum limit model, where we describe the elasticity of the system by a certain set of elastic constant. And you can see that with the increase of pressure, there's definitely an increase of certain elastic constant. And that tells you the system basically going through evolution, going from a more like van der Waals type interaction and suddenly into a kind of quasi-covalent domain. But that happens well before the phase transition itself. Okay. So we are still working on further interpretation of the data, and we try to see if we can reproduce a similar behavior in different type of 2D van der Waals compounds. But we are also interested in seeing, what happens if we look at the temperature dependence of similar phonon mode. And that's actually what we did for different system, the tungsten selenide. And in this case, again, we're going to, what I'm showing here is some in-glass X-ray measurement we did in tungsten selenide. And this wasn't previously measured under different temperatures. So we're trying to do a temperature dependence study on it. And but before I go any further, I want to highlight one important observation we had. So this is, here I'm showing a calculation of DFT versus our in-glass X-ray measurement. But if you dig up the literature, you realize for this tungsten selenide system, most of the DFT calculation were performed for monolayer. And turns out if you do the same calculation for monolayer, our observed in-glass scattering result actually agrees equally well with monolayer calculation. So what I'm saying is, we actually cannot tell by our in-glass X-ray scattering measurement if its agreement with monolayer or bulk is better. So that tells you how close phonons behave in those two types of systems. The van der Waals interactions are quite weak in between the layers, and it's the pressure that actually going to tune it more covalent-like. But before you apply pressure, it's actually very weakly bonded, and you can almost understand the monolayer property, lattice dynamics properties by looking at the bulk. So here's what we are trying to do in this system. And on the right-hand side, I'm showing some of the temperature dependence results. And there are clear stiffening of the transverse optical mode, acoustic mode, or if you decrease the temperature. The data is still kind of scattered all over the place. That's mostly because some of the points, especially the high energy point, our energy resolution is that relatively coarse. On the other hand, the phonons are kind of broad, but the trend is pretty clear. And if you look at Z mode, on the other hand, we see an anomalous effect at low Qs for Q point near gamma point, near the center of the Berlin zone. And those data quality actually are quite good, as you can see on the left-hand side, and the fits over those peaks, both on the positive and energy gain and the energy loss side, are pretty accurate. And we repeat this in several Berlin zones. The results are reliable, and we can clearly see that for Z mode, which is a flexor mode, by increasing the temperature, by decreasing temperature, actually the phonon mode will soften. And on the other hand, if we heat the system up, the phonon mode actually will harden. So what I'm saying here is the phonon become more covalent-like, or the van der Waals interaction is become more covalent-like between the layers for the flexor mode when the temperature is higher. And when it's colder, it's pretty pushing closer to the quantum limit where the mode that become more van der Waals-like bonded. Okay, so if we try to extrapolate to the Grüneisen parameter using the thermal expansion of the material, and we can see that for those Z mode, here I'm again overplotting the data, the point extrapolated from an inlet X-ray scattering versus what we calculate through quasi-harmonic approximation with DFT. You can see there's definitely strong disagreement between those two. But one thing in common is we're going to see a divergence of this Grüneisen parameter at regions very close to the zone center, which is the gamma point here. And by the way, the Grüneisen parameter describes how the energy of the phonon will change in response to the volume change. And in this case, we are looking at not the traditional Grüneisen parameter. We're looking at its temperature equivalent. Basically, we are trying to evaluate how much the energy varies in response to the thermal expansion in the process. But you got a similar idea. And this is the big disagreement between this mirrored data point versus our calculation show that this is a very strongly unharmonic phonon mode. And that's kind of expected since all those flexor modes are weakly bonded and their mode potentials are kind of have higher order force component, large higher order force component than their harmonic part. And our phonon life calculation clearly also indicate that, well, this is plotted for different branches, so you can see for different colors, but it's hard to see here, but what you can tell, if, well, you have to believe what I'm telling you is this particular Z mode actually have very, very short lifetime in comparison with, sorry, very, very long lifetime. In return, you got very narrow phonon line width in comparison with other acoustic phonon. So what we are trying to see here is how much this flexor mode could contribute in terms of thermal transport. There are a few ways it can do, because this type of phonons actually can both enhance or suppress phonon transport. Because at low temperatures, usually you do need a certain sizable phonon population in order to carry enough heat. And lower energy phonons helps on that. And those lower energy acoustic phonon by the flexor mode, they can be easily populated even with relatively low thermal excitation. So that may allow the system to transport more heat at low temperature. But on the other hand, since those phonons have very low acoustic acoustic group phonon group velocity. So that adding a limiting factor of how much heat can be transported. Those are soft phonon modes still. And on the other hand, those nonlinear acoustic phonon dispersion could really complicate the phonon scattering phase space, which is another major factor in determining thermal transport. So we're still trying to figure out if this is, if we have a better understanding of how this could cause some exotic phonon dynamics, and that might be quite exciting to understand. And so in summary, we see a very large harmonicity in terms of flexure mode that involves the autoplane atomic vibrations. And we can easily attune that with pressure. And we actually can observe some transition into a more like covalent bonding well below the phase transition. So that actually is interesting. So the phase transition might not be directly driven by this covalent bonding, at least not under the same, not in the same pressure region we were talking about. Okay. So let me see. Yeah, I actually put a little bit behind my time. So I do want to show a little bit our work on the chiral phonons and the lattice angular momentum. This is not directly related to high pressure, but this was actually quite related to the transition metal Dichalcogenides, because this in those systems, if you look at the monolayer, we do have phonons with angular momentum. So this is a little bit background. And we do know that lattice vibration in structures that actually can carry angular momentum. So if you forget about all those theories in phonon lattice dynamics, just look at the vibration itself, you can certainly create some kind of circular motions in lattice, and that will have angular momentum for sure. The real question is, can you make them icon vectors? Well, it turned out, yes, you can make them icon vectors, but you have to break certain symmetries to do that. And then it comes with questions of, can we observe them, and what are the consequences when you look at them? So here's what I want to introduce very briefly. So if you look at 2D structures like the one I'm showing on the right lower corner, it turns out, yes, you can do that. And this is actually one of the icon mode for phonons. It does carry angular momentum, you can clearly see. And we can actually achieve the same thing with 3D structure. We can only do them for certain limited phase group and with broken center inversion symmetry, but it can be done. And you know those phonons actually going to have icon vectors that have an imaginary part, which is basically a phase factor telling you those are the icon vectors that carry angular momentum. And it turns out they even carry magnetic moments, but those are extremely small, so we won't worry about those. Those are so small, in a sense, you won't be able to see them with neutron scattering. You won't see any of those from X-ray scattering, no matter which one you are looking at. But those are actually the phonon that can have angular momentum. So then it comes up to the system we're working with, where we actually find out there are only limited material that taking the symmetry group we are interested. And tungsten carbide is one of those we can easily get access to single crystals. So here I'm showing the small single crystal we did with index X-ray. And this is basically what the lattice will look like. And if you spend some time looking at it, you can tell, oh, there is a broken inversion symmetry somewhere, and you cannot reproduce the periodicity of lattice by doing a reversion, a spatial inversion operation. And here I'm showing our calculation versus our measurement, and also overplotted with some literature calculation. It turned out nobody actually looked at phonon in this system before. So we are the first one did the phonon measurement. And our calculation agrees reasonably well with measurement. There are more better agreement along certain asymmetry directions versus other, but nothing too dramatic. But what I want to point out is, at this K point, which is at the very edge of the Brilliant zone, there are actually, because of broken inversion symmetry, those K and K prime points are non-equivalent. So what does that tell us is if you look at the right-hand side, if we try to plot the angular part of the phonon momentum, and you realize those momentum reach their maximum value at this key point. And if we visualize those phonon modes, it turns out those two phonon modes are 100% circular, which means those two phonon modes here, one of them will correspond to a right-hand circular motion for one set of the atoms, and the other one will correspond to a different circular motion. And those two modes are non-degenerate. They actually have a slightly different energy, and those energy difference is something we can resolve with in-line scattering. So we thought, oh, this is great. We're going to look at with in-line scattering and try to figure out if we can actually see them by scattering. Honestly, I wasn't optimistic we were going to see anything, since when we do in-line accurate scattering, at least in the non-resonant in-line scattering related to phonons, we treat the photons as just a particle, like a classical particle that's scattering off some potential wall. And the scattering theory doesn't really take into account the polarization or any detailed interactions. But we tried it anyway and want to see if there's anything exciting we can find. And yeah, I'm going to skip this. And this is basically what the existing in-line accurate scattering theory does. And the key part is about this term, which is a dot product of the photon wave vector change, which is a big Q, and this E here is the phonon icon vector. And as you can easily tell, there's actually no part of this scattering dynamic structure factor in taking into consideration of the polarization of the photons in this process. So that's actually not considered. So this is what we find when we put the basal plane of the lattice in the scattering plane. So here I'm trying to show what the scattering geometry is. Basically this K in, K out, and the wave vector of the phonon all in this basal plane here, okay? And we look at many K and K point, and we are plotting our measurement versus the calculation. And you can see the dashed line is actually our calculation. So the take-home message is, okay, if we do scattering along the basal plane, the theory predicts everything pretty well. And we can tell the relative intensity between this TA and LA phonon modes. One of them will be left-hand side circular polarized, and the other will be right-hand side, right-hand circular polarized. And we can predict their intensity really well. That's not exciting. So when we came home with this data, we thought, oh, maybe we just not seeing anything. Then we spend more time thinking about what we realize is all those phonon modes, if you think about them, they actually have a circular motion in plane. So that might not couple with the photon very well. So what we want to do is we were going to flip the crystal and do a scattering that is not in the basal plane. So that's what we did next. And it turned out, right then we see something that is completely different. And here I'm again plotting our measurement versus our calculation. And you can clearly see that in this case, the TA and L modes all agree with what the existing scattering theory tells us. And that's definitely something missing. We definitely missing the the polarization of the photon that might be involved in the transfer of angular momentum during the scattering processes. And we tried that for several different K points and K and K prime points through the Berlin zone, and we see the similar behaviors. So there's a strong indication that we cannot use the existing scattering theory, just like what we did with neutrons. We have to take into consideration that in-line scattering is different. We cannot use the same formalism as we did for neutron for understanding at least the phonon with angular momentum. Okay, and then we think even further. We try to figure out, okay, does this have anything to do with the polarization? And what if we rotate the polarization of X-rays, or if we use circular polarized X-rays? We thought, oh, that might be a fun experiment to work with. But it turns out it's difficult to do it. The reason is we do not have an easy approach to create a wave plate for hard X-rays. And the X-ray we are using is in 24 kilo eV, which is not easily tuned. for polarization. And then we went back through the literature and see how people did it. And turns out for free electron laser, people use a diamond crystal mounted very close to its Bragg condition, and then slightly offset from the Bragg condition to tune the polarization of the hard X-rays. And this can be done because the diamond basically works like a wave plate, and having basically the Bragg diffraction have to happen 45 degrees off the plane that the beam was in. Okay, so and this we actually worked with APS people, Ayman and Thomas, by setting up using what they already have for other beam lines, but we have to tailor it for our applications because now we are working with a much narrower bandwidth. We initially thought this was straightforward, but it's not. It's been cost at least a few beam times before we finally get it working. So what I'm showing here is our measured actually linear part of the polarization and circular part of polarization cross a different offset of this diamond plate through a Bragg angle. And this is actually plotted versus our own calculation based off what people know about these X-rays. So they're actually, I think the tricky part comes from the reason that many EV bandwidth X-ray beams are much more difficult to deal with. Maybe there are just larger angular divergence, or maybe that has something to do with the bandwidth itself. But you can tell that even with our best trial, the experiment only agrees partially well with the calculation, but we definitely lose a lot of fine resolution in terms of control on the polarization. But that's a hope. We hope we achieve a fully circularized beam near here, right-hand side, and right-hand circular polarized beam here, and left-hand polarized beam here. And in principle, we should be able to achieve a rotation of the linear polarization too, but we didn't try to do that yet. So, and I want to show, then once we got this, and we think, oh, let's play with the circular polarized X-ray, see what we can do when we do in-laser X scattering with it. So here's some preliminary results. And honestly, the statistic is still kind of bad, but I'm just trying to show it anyway. So in the center, we are showing the blue line here, we're showing the beam that is completely in non-circular polarized regime. And on the top and at the bottom, we're showing two different degrees of circular polarization. Our hope is we have the largest component of circular polarization for the black ones on the top and the bottom. And the red curves are showing something that is intermediate. This experiment turned out to be extremely flux limited because we lost a lot of more intensities by having the beam through the polarizer. And each of the spectrum is integrated over probably 30 different scans. And then we are really fighting the background. A lot of background actually come from the cosmic rays because now with this statistic, we're looking at the same signal counting statistics as a background of cosmic radiation. So we really have to find a way to block those. But once we remove those, we think we see some kind of weak dependence between those two. Keep in mind, for each of the side, we are actually rotating the diamond plates to different, we are rotating the diamond plates to two different sides. So any inconsistency in terms of the beam geometry or other things shouldn't show up as a symmetric in our response. So we are kind of confident that what we see is more fundamental to the material inside some artifact because of the diamond polarizer. And in this case, what we see is there's definitely a change of the intensity ratio between this LA and the TA mode. In particular, if you look at the spectrum with the largest circular component, there's definitely a suppression of this TA intensity as you can see here, and this LA intensity is somehow got larger. And if we plot the ratio between this LA and TA intensities, the ratio actually goes from somewhere near 3 to about 5 once we have the beam that is circularly, well, we believe it has a big part of circular polarization. It's definitely not going to be 100% circular polarized, but that's what we can do at the moment. Okay, so the conclusion is we see some strong polarization dependence of the LATO intensity. We're still kind of statistically limited, but something is going on, and we're still trying to interpret the result, because honestly, the result is not what we were expecting. We were expecting more like a straightforward selection rule, like certain circular polarization may be able to excite certain phonon polarization more effective than the other, but we're actually not seeing that. Okay, so, and I think that, yeah, that here come to the conclusion slide on the second, the last part of my talk. And we definitely show that we cannot use the same intersectory scattering people been using for neutrons to evaluate the scattering intensity for the phonon modes. And we should be able to generate circular polarized X-rays with MEV bandwidth, but it's actually a very difficult work to do. And we are still not sure how good the beams are. And we do see anomalous scattering, either with linear X-rays or circular polarized X-rays, and that cannot be explained by the existing theory. So there are a lot of questions coming from this. We need to figure out what are the rules that are governing the scattering processes. And the more fundamental question is, okay, now if we look at this, we have to think about how the photon are exciting those phonons when the phonon do have angular momentum. Then the question becomes, okay, is there a transfer of angular momentum through the scattering process, or this doesn't happen? It's really, we're creating multiple phonons simultaneously, which compensate each other in terms of angular momentum. The angular momentum have to conserve eventually, but how this is done. And the last is more derived problem that's more on the material side. And so assume that if we are able to probe the chirality of the phonons, what can we do with this? Is there a way we can use this a way to control phonon-phonon interactions? For example, is there a way we can actually create a protected phonon state by working with their chirality? And maybe we can use this way to suppress or enhance certain phonon-phonon interactions, and which can have implication either on thermal transport or on other things like even spin phonon interactions. Because spin does carry spin does carry angular momentum, and the magnon does carry angular momentum. Now that might be something that's also relevant in terms of the interactions. Okay, I think that's all I had for today. Sorry, I'm running for a few minutes late, and I'm open to any questions. Thank you.
Thank you, Chen, for a very elegant talk. These are beautiful measurements. You're really pushing the technique as well as the theory here with these studies of chiral phonon scattering. So are there questions for Chen? I see one already. Just unmute yourself. Brent.
Yeah, Chen, I think getting back to the first part about the flexural modes, you seem to find that they have rather long lifetimes, yet they're rather anharmonic. You have an idea that maybe this could be a bonding change, since it also tracks the pressure, where you get something a little more covalent-like. So maybe with higher amplitudes at higher temperatures, we're also changing maybe some partial electron transfer between layers. But I'm wondering, is that going to, can you think of how that might not affect other modes? So the lifetime could be very long, even though the potential is kind of strange.
Yeah, thank you, Brent. That's actually a very good question. We are puzzled with that too. This mode has to be very anharmonic. Even when we do frozen phonon calculation on that mode, we know the potential would be very different, very far away from what you would see in a quadratic potential wall. So it's still, we still don't know why, but my speculation is it has something to do with scattering phase space. So even if this mode is highly harmonic, but since there's no lower energy mode, this phonon can easily decay into, or that might have something to do with it. And also you can see the optical phonon actually are relatively high. So they put it in energy, they don't couple readily. We're actually looking into some other system that the optical and acoustic phonon can some partially overlap. And the hope is there might be more interaction so we can actually extract a reasonable lifetime out of those. But on the other hand, ENS actually doesn't have good energy resolution to probe a phonon lifetime. So we are only giving a upper limit, I would say. So yeah, it could be the phonon are reasonably scattered, but just not as broad as some of the other ones.
Okay, thanks. Yeah.
Thanks. More questions? So looking to the future, what do you think APSU will provide in the way of these experiments, new capabilities or possibilities, especially for the chiral phonon scattering?
Yeah, we are definitely starved with flux. Seem like right now, there is not much we can do with circular polarized X-rays, at least for non-resonant inelastic X-ray scattering, since the intensity is just not there for us to do anything. So any increase in flux would definitely help. And we probably have to work from ground up in designing the diamond wave plate in a better way that optimizes operation for milli-eV bandwidth. And that might open a new idea that what can be done. So if we, if this allowed us to look at chiral phonons, and we can see that, let's say, then we can spend more effort in terms of understanding their dynamics and what they can do in terms of a phonon-phonon interaction. But right now, even trying to figure out what are the scattering rules governing the process is tricky with the limited statistics we have. For example, we only look at K prime point, and to get a good idea on how it behaves, we have to go elsewhere. But elsewhere, we're going to have much lower parts of the phonon that are circular. Then the contrast will be even lower. We probably won't even see an effect at those places. Yeah. So yeah, the flux would help, and we could also work with with more focused beam that is more beamline specific inside of the overall update to the facility.
Mm-hmm. There are more questions or comments?
I have a question. Maybe I should.
Go ahead, Arjun.
This is Arjan, yeah. Thank you, Chen. This is really a beautiful talk. My question was more related to the linear polarization experiments. You were showing some results on molybdenum sulfide or mentioning molybdenum sulfide. So molybdenum sulfide is a well-known lubricant under high pressure. Do your studies provide any insight why it is so?
Oh, that's actually a very good question. Honestly, I don't know. And we probably should look at more broadly the layered materials, and that might have something to do. I would say might have something to do with how the forces in that system in response with pressure. I imagine it. At least they won't go covalent as quickly as the tungsten. Well, palladium selenide is the one we are talking about. Yeah. Otherwise, it won't have that good behavior if it's start losing it very quickly.
Thanks.
Any more questions? Okay, if not, thank you, Chen, for a beautiful talk. And thank you all for joining us. We'll see you next week.
Bye.